let's start with the 6th week of our lesson with the math recap. So basically today we will not be doing anything super new, but we will look at what we did last classes, the last 2 or 3 classes, and then kind of have a small recap, which should bring everyone to the same place, hopefully, and then also, reinforce the memories of what we actually studied. And then we will look at a little bit of coding as well in the end. So the 2 things that we will be repeating today will be logic formulas and state machines. And for programming, we will look at the state machines project. And I rewrote the starter codes into Colab, which sadly it no longer works with like the nice matplotlib screen that you can actually like interact with or show images on or play music with Pygame, but it's still working as a demo. And then you can kind of copy paste the programming logic, put it in the rest of your code with your local machine, and then you could actually see how it's working with some visual output with GUI. Okay, so let's continue. Let's start maybe with like the motivation for why are we even studying all of this. So why do we care about logic, and why am I asking you again and again kind of to just fill in the stupid tables with a bunch of zeros and ones, when I mean like the small steps are really simple, and even the solving the questions is actually also really simple. So why do we spend time on it? So the reason is because the concepts keep appearing again and again in programming, and one of them is the FPGAs, which is field programmable gate arrays. So sort of this thingy, this circuit board, and what it does is that it has a bunch of these logic blocks inside of it, and then programmatically, so you upload some software on it, you upload your current version of code, and it will on the fly wire these blocks together however you want it to, and these will be able to execute a program. So if you remember, we spoke a little bit about how every logical kind of operator, so ANDs, ORs, XORs, all of those can be kind of made just from combination of NANDs, not AND, NANDs, and from these you can then start building up more and more complicated formulas. And so this sort of has the similar structure. These logic blocks, I don't think that they would be just NANDs, because then it would be probably pretty inefficient, but I guess it has like a reserved amount of ANDs, reserved amount of ORs, or actually even the blocks themselves might be programmable. So you kind of load an image on it and it will burn or like make a circuit inside. And so why this is cool, besides the obvious reasons, I mean, why is it kind of interesting from useful cases, is that these when they build these logical paths from on the fly, sort of like build hardware from software that you have given it, that then these become really fast and very energy efficient. I think it's because it's just basically connection of direct circuits, and sort of you are giving it something in and then getting the outputs at the end, and it just flows the the energy or like some clock cycle, some like signal, I guess. It propagates the signal through this circuit and just gets it out, and this simulates whatever function you upload it with, and so you don't have to kind of simulate the whole CPU computer, which at the same time as showing you maybe this presentation, it's also secretly upgrading Windows 10 because they are evil, and also secretly maybe sharing this screen that I'm now having, and so like all sorts of things are happening in PC, and so that makes it really I mean, not inefficient because we need that from a PC, but it means that there is a lot of other stuff happening at the same time. And so when we want to make a, I don't know, a cool machine learning application, and we want it to do just one thing, then we don't really need it to be, I don't know, managing Linux at the same time and managing all the stuff, all like inputs, outputs, showing it to the screen. We don't need any of that. And so something like this board, can actually have the same kind of operation in this circuit, which has been programmed to do whatever we want, and then it's doing the same thing without any kind of distractions. So in turn, this is very fast and quite energy efficient. So there is quite like maybe 2 to 3 years ago, I was in a lab where they were doing a lot of research to try to push basic operations into these FPGAs. I have no idea where they moved with it, probably quite far, but this is the way how you kind of can make a box hardware thingy that can be dedicated to do your operations. And the advantages then are that it's much faster and much kind of energy efficient, which is the way to go, I guess, if you want to deploy these models somewhere in the city and have it sort of like, I don't know, map the circulation of cars or something, right? And so in all of this, you don't really have to be sitting with like a long paper and just drawing these formulas by hand, or you don't have to do it really fast either. But the reason why we are studying about it is that I would like you to know the concepts about this and sort of understand how even from some simple operators you can kind of build up something more complicated. So that's the motivation for the logic. And when we go into state machines, so why do we care about state machines? Because of history of computer sciences, yes, but also because it is actually being useful. It's actually being used in all sorts of places. So, for example, games, or in places where you need to design some sort of behavior. And you have some simple blocks and then they kind of accumulate into something more complicated. And as we were saying in the previous classes before, this is quite heavily inspired by something happening in the nature already. So this is some protein synthesis, new protein synthesis. So there is sort of RNA contains a code and it goes through and sort of this code influences whatever is being created. So you could consider this a signal and you could consider all the chemicals around this thing, around this CPU, I guess, as a, or it's an enzyme, I think, as a program. And so then this thing creates a new thing. And so studying about state machines, even in a very simplified form, maybe helps us understand why something like this would be possible, and maybe helps us a bit more to appreciate the beauty of it, I guess, as well. And in theory, I guess you could also start simulating something like this with some smaller, simpler state machine blocks. So yeah, basically that's it. That's what I wrote here as well. Understanding and modeling biological processes, but also just because of the reasons of history of CS, computer sciences, this was sort of a way how to do some programming, because before there were even some computers. So in the real world there were some ideas about them, designs again, but something like Turing machines were a suggestion before this. So again, it's kind of interesting to know about these concepts if you are entering the whole field, I guess. And then also they are useful, I think. So you all remember how to do logic formulas. It's basically by having a big table and then enumerating all possible variable values, sort of at the left, and then just propagating these until you get into the expression that you want to get into. Right, so we will see that again for maybe whoever was not here in the previous classes, or if you need some recap, I will do one of them kind of here on the board. And then I will try to do a Blackboard hack by separating you into groups and hopefully having you do some tasks kind of in smaller groups. Okay, so when you are working, this can help you as a sort of cheat sheet, which is just translating all the possible operations that we have, the operators. So be it the not operator, the and, the or. I guess like a bunch of these we already know. I remember the implications were slightly more complicated, so what it means, I mean, like I found a definition for the implication. Implication means that the statement, if A is true, then B is also true, is either true or false. So that kind of explains a bit more why there are these two ones in here. So because if we are checking for this statement, if A is true, then B is also true, this makes sense in these two cases. So if A is true and then B is also true, if that's, I mean, this is clearly not the case here, so here is 0, but here, if A is true, then B is also true, is actually correct for this one. But if we are checking the same sentence or the same statement in these above, they don't, I mean, this doesn't say anything about A being 0. So it's not false to say in this case, if A is true, then B is also true if both are false. Because we are only kind of trying to, we are only trying to catch the, this case, basically. So yeah, I mean, implication is a bit weird, but this sort of maybe should help a bit. And then the last one of the simple, of the basic ones is the equality, and that means basically both of them are the same. And then we have some slightly more complicated ones, but still, just additions to the basic ones. That would be exclusive OR, which is true only in the cases that one or the other is true, not when both are the same, or both are 1 or both are 2. Then an AND and NOR, which is negative of and negative of OR. So you can look here, this is basically the same thing as here. And the reason why, I guess you could always write it as A and B and then a negative before it, but that's a lot of signs, and sometimes you need to be kind of concise, so you just write none. Yeah, and the same with NOR, it's just the negative of OR. So last class you saw how we are kind of just propagating how we are evaluating one logical formula, but what you can do as a task is kind of trying to evaluate if two of these formulas have the same logical evaluations. And that's something that's more interesting, I guess, because if you are just evaluating one formula, you can just go from left to right, and then you arrive at some conclusion, and you end up with like a bunch of numbers, and then that's your logical evaluation for all the possible entries. But that's not so interesting. What is a bit more interesting is this one, where we are comparing two different logical formulas, and this special sign, 3 equals or 3 lines equals, means the logical equivalence, and that means if their tables are exactly the same. And so that can be used to somehow maybe test some properties of these operators, that as we will see later. But yeah, let's start with the task 1, and this one I will do sort of with you. We would like to use we would like to answer if these two are the same. And in order to do that, I guess I will mess around with the boxes. I guess I will. Okay, this copy is the same style. I will build the small building blocks that we need to answer this in here before it, right? So I can kind of like write the evaluation for A or B, then A and B, and then eventually A XOR B. And so for the OR operator, so this would be, I can even like write it here. OR is like in Python, A or B, basically. So this thing would be true in this case, and this case. It wouldn't be true if both of them are false. So this is how we arrive to the first one. This we can rewrite as if A and B. And so this wouldn't be true here. So if false and true will still evaluate into false here as well, and here as true. And so I'm always looking at these two previous values and then kind of like substituting it into this and then getting the answer. So I don't know how exclusive OR is done in Python, but exclusive OR basically is that at least one of them has to be 1, but exactly one of them has to be 1. So not both, basically. So they cannot be the same. So it will be true only for these two. So in this case, it's 0 XOR 0 will be also false, and in this case, 1 XOR 1 will still be 0, because we want the exclusive, or we want just one of them being true, not both. Okay, and so the operator, yeah, we somehow want to reach. We are going from left to right, and we want to reach these two evaluations. So I have written this one here, so I can like just copy it. But to get to this one, I need to negate whatever we have in this column. So if I say basically of hop, and then right here like column E, right? This is something like just referring to it. On a paper I would make an arrow, right? So this is a negation of something what we had before. So it's just flipping the zeros into ones and ones to zeros. 1, 1, 1, 0. Because it's just referring to this. And so this is the same as writing this. Nice. And then for the last bit, we somehow still want to make up this whole expression, and it's built from two parts. From one OR, which we have here, and then from one this thing, which we have here. And so how to rewrite it would be to say if the value in D or and the value in G, right? Because it's saying if this thing, it's the D, the column letter D, and G, so this column, and they have to be evaluated as using the operator and so we will be using the same evaluation as in this case. We were also like doing AND. So this is again something we would have variables sort of like A and B. Instead of A and B, we could have these variables as referring to these two blocks. And so this also rewrites to having this and this, right? And then I'm writing the AND on purpose large here because I can then change it to this. And so this is exactly the same thing as what we want to arrive at in the last one. And AND is really easy. AND is being evaluated as both of the values that come into it. Oh yeah, I will even like, wait, kill these two. Yeah, both of these two values have to be 1 for this to be true, because that's how AND evaluates normally. So 0 and 1 is 0. 1 and 1 is 1. 1 and 1 would be again 1, and then 1 and 0 would be again 0. Yeah? Yeah, just one thing to kind of explain. The letter T here means the true, the absolute true, that is true on all occasions. So if we are filling it in this board, and then look at the task 1A, then true will basically mean once everywhere. This is absolute true, which is true regardless of what the A and B is. The same like F would be all zeros everywhere. Okay. So this is task 1. Yeah, it should be like some of them are a little bit more hard, some of them are still relatively easy. Yeah, you will see. Then the task number 2 is a slightly more interesting one, I guess, because we are trying to figure out if this operator or distributes in this way. So if I have some expression here that has 2 parts, and then I want to kind of multiply it with this expression or before it, if this is something that we can do, if we can kind of take this part and then shove it before the A, and then take this part again and shove it before the B, getting this. So and then kind of just having this one operator here, which we had between these two, and then put it, kind of keep it here. And sort of if you imagine that these were not ors and ands, but for example the multiplication, so like a small star, this would be something that would be true if we are multiplying like C times A plus B. This is true that that equals C times A plus C times B. But the question really is if this is also true for these special formulas. And so this is something that we kind of want to check as a property of the operators. And that's something kind of more complicated and kind of, I guess this is actually the algebra part of this this whole example, or these whole tasks, because we are kind of trying to check for this one property. This property is called distributive property, and multiplication actually has it. And so the answer for task 2 is to check if it's also true for the for this one, for the OR. And this might look slightly more complicated than what we were doing here. However, it's actually the same, because you want to, at the end of the road, you want to just check if this thing is the same as this thing with all of its evaluations. So if for all of the possible inputs, if these two are equivalent logical formulas. And so this is something that we have been just doing. You can just have A being this and then B being this. And I also highlighted by color how this is the multiplication, kind of how this steps in. And then you are just checking if this is true for these two. And so this is by applying the same stupid rules, just propagating zeros and ones to the right, but then arriving at a quality that you can kind of or a property to actually like proving that this operator has this property or doesn't. And so if you think that these two are the same, then it will be actually true. So this is slightly more exciting. Task number 3 and 4 are easier. I think the most work is the task number 1 and task number 2. So don't worry, task 3 and 4 will be easier. And that's to kind of illustrate that there is a strange behavior in a large row of ends. So let's say that we have a long, potentially very long, potentially even infinite almost row of some expressions and then ends in between them. And we kind of want to figure out how to evaluate this whole expression fast. And the trick to evaluating this is to make advantage of how ends work. And so if just even one of these expressions inside of this is false, it will kind of eat all the other truths and they don't matter at all. And then it will evaluate into false. So this is the same as if we had like bunch of numbers here, whatever the numbers were, and some would be really complicated to calculate, right? There are some like, I don't know, something really complicated to evaluate. And if at least one of them is 0 and we are multiplying all of them, then we don't care about multiplying anything with 0, because it will end up being 0 in the end, regardless of what the individual parts were. I think there is some slight exception to when we are multiplying infinities with zeros, because that is not allowed or something, but let's not go there. So in algebra, for multiplication, this is called an absorbing element, and also for these expressions, it's also kind of false would be an absorbing element for ends, I guess. And so how to convert this into a task? So find one element which always evaluates as false in this very long formula. It's not super long, and it's also not super hard to find, but it just should illustrate that. Imagine that this one is really hard for us to kind of take the paper and evaluate everything. You just need to find one of them which always evaluates as false, and then you know that all of this evaluates to false nonetheless. So we don't really care about the possible like a being 1 or 0. We just want to find one of these expressions that always, regardless of the values, evaluates into false. Okay. So yeah, I mean, I put this near the end of the tasks on purpose, because if you get stuck with it, it doesn't matter. I can just explain it later when we are looking at the exam at the solutions. And so task number 4 is basically the same thing. However, we are looking at a long, potentially very long, potentially almost infinite row of expressions, and then ORs in between them. So having these ORs. And the trick there, again, you can imagine that these are not just simple falses, but they are something more complicated. If at least one of them is true, then we don't care at all about the rest of it. So then it would again evaluate into true, regardless of everything else. Oh yeah, there's one extra, or I should erase it. Anyway, so in this case, the true works like the absorbing element. So similarly, like in the previous case, in the previous task, the task here is to find one element of these, which would always evaluate into true. And then you can say, hey, I don't care about none of the rest. I know that this will always be true, because the one true will eat up all the other falses, because we have the ORs in between, right? So maybe I said it too fast, and maybe it's slightly confusing. I will show it again when we have the solutions. So don't worry about tasks 3 and 4 too much, but if you can get it, that's great. Okay, and so in order to do that, we will have to kind of unpack this whole thing, and so we can kind of go from inside out. So I guess I would start with A or B, then do the A and whatever this column will be, then the last one here. I guess also, yeah, I will start with that. So let's do A or B. I will be doing this relatively fast, so if there is some like hesitation somewhere, or if there's some stuff which is not clear, please ask me and I can go slower over that. So A or B will be true for all of these, because at least one of them is true. It's not exclusive of when this one will be true. And then let's say A, and I will have to copy that one. But yeah, basically let's say, what about this one? And that's checking this column and this column. And so we are we want to do AND, which will be 0 and 0 is false, or like false is false. 0 false and true is still false. True and true is true currently. True and true is again true. So this is this part. And then let's check not A or this thing. So I will write not A here first, maybe. And not A is just negating whatever was here. So 1, 1, 0, 0. And then finally, I will highlight these. We care about the or between these two columns. So it's basically column. I mean, if I'm writing it here, if column F or column G will be basically this expression, and correctly like to write it there. And yeah, so 0 or 1 is 1, and that's basically the same here, and the same here, and the same here. So when we look at all of these evaluations, and then all of these evaluations, we can see that they are the same. So the answer for the task 1, A, would be that yes, they are all the same. So that was, yeah, this was this. Okay, if you look at the task 1B, it's slightly more complicated because we have C as well, so we need to look at all the possible evaluations for C. Yeah, I'm recording, just I was just checking. So in here, it's relatively easy just to check the values. We don't have to kind of unpack it. So as I was saying later in the task 3 and 4, we will see that if we want AND between all of these, this will be true only if all of them are 1, because the first part will be basically true even when just the 2 of them are 1, but the last one would be negated if this was false. So we can kind of just like hack it a little bit and just look at all of these values and then say that kind of like if you write it as an expression, if A and B and C, we know that in Python this will be evaluated as true only in the case that all of them are true. So this is true only here, which is a faster way how to do all of that. And so here all of them are. So I will just fill this. And so now we want to check if these two expressions are the same. So kind of again how to evaluate this one. We have ORs in between them, and so we know that this whole thing will be true if at least one of those will be true. So if I were to write it in Python again, the same kind of if A or B or C, this would be true if at least one of them is true. So it's not true here, but with all the rest, it's actually true because at least one of them is always somehow true. So let's say 1, 1, 1, 1, 1, 1, 1, and both of them are quite nice, right? But they are definitely not the same. So that's the answer for the task 1, is that these two are not the same. The expressions are not the same. Okay, so let's go to the task number 2. And that one was, well, basically still the same thing as we were doing before. But this time there was kind of a meaning behind this. So let's just check these two formulas and do them here. So what will be useful? It will be useful to have probably A and B, right? Extracted. And maybe C or A, and then maybe C or B, because these two are the building blocks for this one. Okay, and so yeah, let's just do this. Kind of for this whole row, we don't care about the C value at all, so we will know that this one will be the same as here. So A and B will be true only if both A and B are 1. So here and here. Right, and everything else is 0. Okay. This one. Okay, all of these. Okay, for OR between C and A, we want at least one of them to be true. So not these. These ones, yes, because the A is true. Then these one also true because these one are true as well. And then the last two are also true because both of these are true. So at least one has to be, and then both of them are, both A and C are true. So we can just evaluate it as a true. Please control me if I'm making some mistakes or something. I'm like slightly aware that doing it on the board might not be the best. And so now in this case, we are looking at C or B. In that case, we are looking at these two columns, and we want at least one of those numbers to be 1. So 0 or 0 will be 0. Here, at least one of them is 1 here. Cool. This one is again nothing. At least this one is again 1. This one again 1. And then if we see here, all of them have at least 1. So we can keep. And so now we want to kind of build these two. Let's start with this one. So it's C or A and B. So these are these two columns. And we have OR between them. So let's call it like this. And we can directly start writing here. We want this one or this one. So if I were to write it in Python, I could say something like if or E. And let's say that these are the two values. I mean, let's say that we are always saving these two numbers into the variables D and E and then just evaluating it here, right? So if this one or this one is 0, it's 0 again, 0 again, and here we have 1, 1 at least, so that would be 1. And then in all of these, there is at least 1, 1, so we can also evaluate them as 1. Okay, so let me mark this one as this color. In the second case, we are looking at C or A and C or B, so these two columns. So, and in between them, there has to be AND. So let's color them, I don't know, let's see, like this. And in this case, we care about AND between these two columns. So if F and G. So this will be true only in the cases that both of them are 1, both of the inputs. So this is not true, this is also not true, this is also not true. But then we can see that all of these are actually 1. Because both of the inputs are 1. Right? And finally, when we look at these two results, they are exactly the same for both of the formulas. So the answer is that it's actually true that these two formulas are logically equal. And this means that this operation OR that we had actually works like a multiplier, because we can multiply brackets with it and then assign this OR for A and then this OR for B. So by doing this, I mean, like, yeah, time consuming but still relatively easy task, we have learned something about the properties of the whole operator, which is kind of interesting. Okay, so if we look at the rest of the tasks, tasks 3 and 4, these two are, I mean, they are there to just prove a point, sort of, just to talk about this this property and the way how we can speed it up by like, instead of evaluating everything in this long chain, just looking at one of them and picking up one which doesn't make sense and then collapsing the whole equation by just picking that one. And so the reason why there is no table anywhere is that I just wanted you to look at each one of these in separation. And so you could look at the tables as well, but like it would take much more time to doing everything one by one. So this is this is A or B, and given the fact that A and B can be, they will be both 0 and 1, so there are the 4 possible values, this whole equation, or like this whole part, this whole bracket, will sometimes be true and sometimes be false. So this doesn't help us really. Let's go to the next one. It's not A or B. This will be again sometimes sometimes this will be true and sometimes this will not be true. So again, this doesn't help us with kind of this trick. If we go next, the question is A and not A. And so this is an interesting nonsense, because we can actually look at this one. And yeah, okay, I will actually write this one as a new formula. Let's do this. And let's evaluate A and not A. Okay, let's task 3. So we have A here. Let's copy not from somewhere, or directly not A. And actually we don't even care about B in this case. So we can delete it, and these two as well. So A is either 0 or 1. And so not A is the same thing, but reverse. So 1 and 0. And so if I am looking at... I think you can see this probably already. But if I say and not A, it will be false here, and it will be false here as well. So basically the whole thing evaluates as false, which is the same as 0, 0. So we can say that this whole expression is the same. So this expression here, A and not A, it does make sense, but it evaluates always to false. So in this case, we know that this guy here in the brackets will always be false. And so we can, by now, we can stop looking at everything else, because if this one is false, and all of the other ones are whatever basically, then and there are ends, this whole formula will evaluate into false. So how is this useful actually? What happens is that sometimes you have these I think that these equations, the things in the brackets, will come in some. You can convert any some existing problems into this strange formulation when it's evaluated as false or true, and then if you solve this long formula, you can go back to your problem, and then it will kind of answer for that problem. And there are some ways how to try to speed up some of these computations, because sometimes these formulas will be really long, but some of them really will have the same form, so there will be lots of ends, and then there will be some complicated things in the brackets. And so the trick there is to maybe spend a little time on all of them and find if there is some nonsense like this, or always false like this, and then you can collapse the whole computation. And so you can see that this is kind of speeding up some longer computation somewhere else. So the same in here. This is the same in here. The same trick, but with ORs, and in this case we again want to look at these. A can be both true or false, so it doesn't help us. We are looking for a permanent true right now. B the same, non-B the same. We have A again, fine. Actually, this one would already be evaluated as true. Okay, that's a bad task then, because this one already is not true or true. Will be true. But yeah, I wanted to show it here, but then we can also just continue. The same applies here. It's not true or true, or not A and true, and A. Sorry. And so let's just try it. Not A and A. Not A or A. Sorry. Let's try it here. We have not A and A here, so let's rename this tasks 3 and 4. If we say A or not A, then we want to see kind of just evaluate this expression, false or true will be true always, and true or false will be true always. So we can see that this one always evaluates the same as a given true. So we know, is it the same? It's not, doesn't matter. So we know that this expression, so this part, or actually even this part, both evaluate as true, and so we don't have to care about the rest of this. Yeah, so basically tasks 3 and 4 were relatively simple, but they were there to prove a point, I guess. Okay. Right, before we go to the state machines, I want to check if everyone is still okay with this. Let's get to the second part of this lecture, and that is to repeat the state machines. Yeah, I hope it's not too time demanding or not too difficult, but we will again go through a very simple kind of state machine example, look how to do it on this screen, I guess, and then split into the groups again, and then try to do some of those examples. I think maybe designing state machines is slightly more creative, so it might be more fun, and trying to figure out what is possible, what is not, maybe. And again, the same way, keep the results. We will be submitting it into the questionnaire. I think the main thing there will be if you were trying to do something, then it's good. It doesn't have to be all done, basically. And then we can, on the screen, kind of go through the solutions as well. Okay, so short recap of what state machines are. So they are machines, sort of like basic simple programming before programming existed, or before computers existed, and they are made of these things. So they're made of states, and this is a set of some states, and one of these states, one of them is the starting one, and that's where the machine is sort of starting, initialized as at, and then there are few accepting states, and well, there doesn't have to be any, but then the machine is useless because it doesn't accept anything. But there can be more than one, because more states can be the ones accepting. When designing state machines, there can be multiple designs doing the same thing. There can be some more efficient, some less efficient. But that's about it. And with the states, to get from one state to another, we need to have some transitions, and transitions are reading some incoming letters that are coming in, and these letters move from one state to another, the whole machine. And it's important to kind of know if the state machine accepts a word, and that happens if this machine ends up in an accepting state after reading this word. So we also made a distinction between two types of machines. One where at every point you know where to go, and there is no kind of hesitation where to go, because if you are in a state whatever and you read A, there is only one arrow going out from this state, so you know you have to go there. But there are some different types of state machines, so-called non-deterministic, where you might have multiple paths from one state accepting the same word. Taking in the same letter and then moving into other states. So there are multiple transitions from one state into other states from after reading one letter. And in that case, we kind of have to try all the possible paths, and then if we end in at least with one of those paths, if we end in an accepting state, we accept that word. So these are harder to evaluate, and or maybe sometimes also harder to check, but it's easier to design with them because you can just split the paths however you want. Okay, so this was very conceptual talking about this. Let's actually go to the example. So this would be a simple state machine. This means that we are starting here. This is the starting state, and this arrow means that this is an accepting state. So we are starting in a state 1 if we read a letter A, then we can either stay in the same state or we can go to the state number 3. And so you would know that this is a non-deterministic state machine because there is a uncertainty where to go. You are, oops, sorry, spoilers. You are going from this state into 2 possible ways. Like you have 2 possible paths to go to. Yeah, and so there is a bridge sort of which would accept B and then stay in there, and then this would be accepted, or there is a path into the sort of like a death state where you don't continue from it, but these words are not accepted. So does anyone have an idea what this this state machine would do? Okay, I will progress the slides then, and then I guess try to explain it. So this state machine is a one which accepts words which contain at least one B. Because if we feed it with something like A, it will always either stay in 1 or go to B because it can, because there is A here or here. But it will never get to an accepting state. If it contains at least one B, it can jump this bridge and then be here. And even though later it can read some A's or something, it will already be with the one B which it needed. So at the start it also could just go here, but as I was saying before, with non-deterministic machines, or in cases where there are multiple paths to take, you have to take both of them and kind of check all the possible results. So this machine will read the one letter B and then use that as a check basically. You are checking if the word that you are giving it has at least one B. Okay? So maybe it was a bit difficult to come to this from the very theoretical explanation before and then just seeing this. So, but this should be clear now, hopefully. So let's look at this another example of a state machine. It's a slight alteration of the previous one, and we have this letter B which gets us from here to here and into an accepting state. But additional B's would kind of move us here. So what does this one sort of do? Any ideas? Okay, yeah, awesome. Yeah, basically yes. So whenever it reads more than one B, it will jump from here to here and then kind of be in a death state, and then it doesn't move on again. And so this is a sort of filter which will just accept words which have exactly one B. Okay. So there is we will be now drawing these ourselves as well. Let's make an agreement that when designing the state machines, you don't have to include all the blind paths. So for example, I was actually not even writing what happens if I'm reading A or B here. It would be staying inside 3. So we can ignore the blind paths. However, if I crossed out the whole state 3 here, then this machine, without the state 3, wouldn't be able to send us from state 2, which is accepting, after reading another B, into the death state. So sometimes we do need this one to actually like make it easier to read the design. So yeah, so let's have an agreement that we can ignore some of the paths, but if there is a, for example, death state that we need, let's just keep it in. Okay. So there are more tasks. In this case, it's 1 to 6 and 7, but the 6 and 7 are kind of just questions, which is not drawing the state machines yourself. And I will draw the first one with you, the task 1, and then we can split again in the same way of drawing the task 2, 3, 4, 5, and then trying to answer the 5 and 6. Oh, 6 and 5. 6 and 7. Sorry. Okay, and so again, drawing state machines is something that maybe requires a Blackboard or something, so I will use a vector software, and I will work with this file that you can find in our GitHub. So you can start, if you have any like vector editing software, you can load the SVG file, or you can load the PDF file. I don't know which one is easier to work with. but I can post the link, I guess, to this one or this one. I don't know which one will load. As a, I think this one will be easier to work with, so I will just send this link. Okay, so I prepared this vector file, which basically has slots for all the tasks, 1, 2, 3, even with the description here, and then some building blocks that you can copy paste from the left and sort of like just, yeah, I don't know. You don't have to use this one. You can also just use your paper or whatever, whichever is easier. I will be using this one because I think it's easy to show you how to build the machine with this software. Any vector editing software should do, or in theory, even if you open the PDF file and just draw with like the Adobe has some sort of way how to just scribble over existing PDF, so you can use that as well. You can also use a paper, you can use whatever you want, it doesn't really matter, but I wanted to, I thought this might be an easy one to use. So let's start with the task number 1, the state machine which accepts words of length 3. And as was said here, unless written differently, and I guess that's just the case of 3 because we have some numbers here, the alphabet, the possible incoming alphabet is A's and B's. So we always have to have a state which we start in, and we want to accept words exact length 3. So whatever is shorter or longer than that, we want to kind of kill, I guess. So if we read, if we are just in the first state, basically here, we cannot make this one accepting, because then it would be accepting even empty words. So right now we cannot end here. We have to go to the next one. Oh, I should have prepared some straight lines as well. Okay, this will be slightly awkward, but still it's okay. And so in here we don't care about which letter it is. It can be A or B. So let's write both of them here. Okay. So reading one letter will get us into the second state. We could have nicknamed the first state sort of as 0 characters read. The second state could be nicknamed as character read. And we will basically repeat the same thing. Unless our computer freezes, which will mean that that using the same method, sort of like after reading any other letter, we move to second, like the next state. So if this one is no letters read, this one is 1 letter read, this one is 2 letters read, then you can kind of guess that you can just enter another one after this and nickname it 3 letters read, and this one will be the one that we want. So let's make it horrible arrow. Let's make this one the accepting state. So 0, 1, 2, 3, and now we kind of have to deal with the situation that we have read any other letters. So add that here, and that will move us into kind of another state, which we want to maybe call death state, which will no longer be accepting. So let's move this one from here, and let's have it here. So after having read whatever kind of string is coming in, if we read 3, it's good, and we see we accept it. If we read any more than that, we will just go to the next one, and that one is no longer accepting. And we can sort of have a we can have like an arrow pointing towards the same state, so staying in there after reading any other letters. So you can imagine that. So we don't have to even do that because we can just that's the one that's not written down. but basically if we get to the death state, we want to stay there. Okay, good. So the other ones, the task number 2 is to draw a machine which will accept a sort of the regular expression A star B B A star. What this means is that A star means any repetition of A's followed by BB and then followed by any repetition of A's again. So just keep in mind that A star also can mean no A's at all, but it should be relatively easy to use in the state machines because basically we care about reading some A's and then exactly 2 B's and then some A's again, and then we are done. I guess if we read something extra after this, which would be for example B, then we would want to end this. Or if we read something wrong in the middle, we can also start ending it. But yeah, let's just you don't have to draw all the states, just the ones that lead you towards the accepting state. Okay, so this one should be relatively easy. The next one is a machine which accepts exactly the pin number. Don't use your pin number, just use like 2020 or something. So this is a design which would be which can be used, for example, in just having like the pin number checker or something, or like a password board. You would be implementing something like that. Just a machine which accepts exact string or exact words. So if it gets 2020, it accepts it. If not, if it's any different or longer, it just goes into the death state. So again, this should be relatively easy. You don't have to write all the letters, all the possible transitions. Just go through like 0, 1, 2, for example. I think even in this board, I have prepared just 0, 1, 2, 3. So you don't have to go too wild with this. Okay. So these ones are kind of the basic ones. For example, if this looks too easy for you, you can also just skip these and then go to these two, and then return to them when you are done with 4 and 5. So the slightly more interesting and creative one is the state machine in task 4, where we want to accept even amounts of A. So that doesn't mean empty. That's not even. I guess 0 is not even. So if we get 2 A's, we want to accept it. If we get 3 A's, we no longer want to accept it. If we get 4 A's, we again want to accept it. And so there is like a nice way how to draw this as a machine, where you want to accept some and not other. And it's also like an illustration that state machines can not just match regular expressions or exact strings, basically. They can also match sort of this function called even. Okay. Task 5 is accept a word if number of A's in this word is less than 3. So, for example, no characters is a string with number of A's less than 3. So you would accept this one. So basically what this means is you can accept the first state that we are in as well. However, basically I guess the A will be the main letter which moves you from one state to another, and in this case, in the task 5, we want to have more than one accepting states, definitely, because we want to differentiate between having read 1 A or 2 A's or 3 A's and accept these states, but not accept anything after that. Okay, so this one should be a bit more fun, these two. The task number 6 is a question to try to figure out if you are given a already existing and working machine accepting some words, how can you modify this machine in an easy way to accept inverse of all those words? So what this means is that if we were to do it with this machine that we just signed in this task 5, how would you very simply modify it into accepting something which has, I guess, just more than 3 A's? And there is like an elegant way how to do this. If you figure it out, then it's great. If you don't, it's okay. I can just then show you on an example as well. But it's kind of like a less manual work, but more thinking about the concepts. This one. Yeah, and you can try it with inverting the machine from task 5. Okay, and the last one is again, this is a bonus question, so it's slightly more advanced as well. It's a question if we can build a state machine which would accept words with less A's than B's. Yeah, so we ended up on the task number 1, which was to design a state machine which accepts a word of like 3. And now we will go to the task 2, which is the same task to design a state machine which accepts the regular expression of however many of A's, then 2 B's, and then however amount of A's again. And that string is something that we can accept. And whatever is not the same as this kind of expression, we don't want to accept it. So as always, we will be starting in some starting state. We don't want this one to be the accepting one. However, we would like to read as many A's as possible in this state. So we can have this guy here, this like arrow pointing into it, saying that if we have however many A's we want, we will still stay in the first state. Then, because there are 2 B's and the amount of them is pretty solid, it's just 2, we can have these 2 sort of states being moved from the initial state into the next one by reading a B. So I will copy these 2. And oh yeah, the copying and pasting seems to be trouble for Inkscape. So I will just draw them anew usually. Okay, so from the first state, after reading a B, we get to the second state. So this is sort of like if we were here in the expression, we have read the however many A's and then 1 B. Okay, so I will try copy pasting the same thing, because then we want the state to be sort of, we want to replicate this, right? We want to have a transition into the next state if we have read another B. So something like this. So if we get all the way to here, it is as if we were reading this and then got all the way to here. So basically, we can already start accepting this state, because this means that we have read many A's, 2 B's, and then no A's to it, which is still okay, because this still kind of fulfills this. A can be also no A. But to add however many A's you want at the end, we also want to add this thing. And so in this moment, we can kind of go here, go here, go here, and then stay for however long, as long as you are reading this. And we somehow want to kill it or go to the death state if we read another letter which would be breaking this formula. And that breaking formula letter would be B, because if you have passed through as many A's as possible, then 1 B, then second B, again repetition of however many A's, and then reading another B, then it would be this regular expression. And I guess we can also add one here, saying that whatever you read here will just keep you in the death state. You don't get to go home again after this. So this is the state machine that we want. So in theory, we can also add links from like this one. If we read A, jump to here, but we can also just like this, because if we are stuck in this case, in this state, we didn't transition again into this accepting one, then it doesn't really matter. So this is the machine which would accept the regular expression of a's, 1, 2, b's, however amount of a's again, and then that's it, nothing more. Okay? Right, so let's get to the next one. I will copy these arrows. So again, I will not be drawing all the possible arrows that would bring us to a death state, because that would be a lot of arrows. I will just make one path, which is for the for accepted string. So if we read first character of it, which is 2, then we progress. If we read another character of it, which is 1, I mean 0, then we don't progress. And I mean, like, you probably know what will follow after this. So 2, 0. And then again 2, 0 again, and then if we read anything else before it, we don't progress, and then probably at the end we want some death state if we read anything additional to that. So yeah, this one was one of the easier tasks. 2, 0, 2. 0 again, and this one will be the accepting one. I guess the idea about for this task was just to illustrate that you can use it as a bin machine, sort of, and then we death state here, which we will use for anything which comes after. So we can write that as like 0 all the way to 9 or something, and this would include any other letters. So of course we can always also have kind of transitions from all of these states into the death state, but we don't have to do that because you don't read. If you have read 1, 2 and nothing else here other than 0, you don't progress. So we are kind of stuck in this one state which doesn't accept anything. So this is the one which would accept the 2, 0, 2, 0. Yeah. So yeah, and now it's getting more interesting because we want to have a machine which accepts even amounts of a's. So yeah, let's start somewhere. This state means I have read nothing yet, so we don't want this one to be accepting. Let's go from this one into another state after reading A. Yeah, this can be here. And this state sort of is, I have read 1A. If you read another A, let's go here. And this one means I have read 2 A's. So this is one of them which we want to accept because that's even. And if we read another A, we sort of want to get back to, not this one, yeah, get back to this, the first state, or the second state, I mean, we draw. And if we have read another A from here, we again get here. So we can sort of start making these two states as, I mean, no letter read, odd amount of A's here, I guess, and then even amount of A's here. And so this one is the state that we want to accept. So there is still something missing from this design, and this is for reading B's, because in any of these states we can just start reading B's, and it doesn't really change what it does with the fact that we are accepting or not accepting the word. because we don't care about the bees in this situation. Sorry, the bees. And so I guess this is it. There might be even more elegant solution to this. I don't know. Yeah. Does the state machine make sense? This is a odd amount of A's, and this is an even amount of A's state. Yeah, good. And then let's get to the fifth state. Fifth task. A state machine which will accept a word if the number of A's in this word is less than 3. Right. So this one was slightly special to the previous cases, in the sense that there will be more accepting states. And as I was writing in the presentation, even a word with no characters is actually a word which would be accepted by this, because the number of A's in that word is less than 3. So even if we read nothing, we already accept it. However, from this point, we have to kind of start moving somewhere, and if we move somewhere too fast or too far away, we no longer want to accept it. So there will be a death state after some moment. Okay, so it's the number of A's we care about. So let's have a transition which is depending on these. So if we read 1A, we got to the read 1A state, I guess, and 1A is still less than 3, which is good. I guess we don't really care about B's in this situation, so we can just like stay in whichever state you want with the B's, and it will not break the functionality. Yep, let's go onward. If we have read 1A, and then we keep reading A's, we can still move into next state. So that would be here. And then again, if this is no red, this means 1A red, and this means 2A's red. 2A's still less than 3. So we can kind of accept this one as well. All right, I forgot to put A here. Okay. And finally, if after reading 1A and 2A's, we read another A, we would like to end in a state which is not that far, which should no longer be accepted. And right, also if we read B's here, it doesn't matter. And also if we read anything else after in this state, we kind of do want to stay there. So I will just paste another arrow pointing back to the same thing. Okay, so we want to stay in the states, in this state with A or B. And so it's interesting to see, because the previous cases were usually something where you had just one state which would be accepting somewhere, like fulfilling some condition which is repeatedly changing, or some like basically exact formula which has been fitted by the machine, and then basically just one state which accepts it. Whereas in this situation, we accept everything up until some moment. Cool. So does this make sense as well? Mm-hmm. Okay. Perfect. Thanks. So this is task 5. This is far as you got, some of you, which is great. And now let's go to the last 2 questions, which were kind of more like a bonus to these. So a machine which would accept the inverse of all words of another machine. I will start with this machine as a to illustrate this idea. Wait for it to copy and paste. Few centuries, and then edit something on the machine. So if this was a machine which would be accepting words with less than 3 A's, the inverse of this would be machine that would accept more than 3 A's, or like more and equal to 3 A's actually, like the inverse of all the words that were accepted in the first machine. And an easy way how to do it is to flip one thing on this machine. All the states which had the accepting state, so all of these, you will delete that accepting state, and for all states which didn't have it, you will actually add the accepting state. So we can add one here and then delete the accepting states here and make no other change to the whole machine. And this inverts sort of the whole world of words which would be accepted by it. So this is like a relatively easy way how to design something, or if you already have something designed, to flip the logic of this machine. You can also design like a problem which is complementary to the one that you are solving, and then flip the accepting states there, and then maybe the machine that you arrive to there is actually more efficient or with less states or something. So this is like a neat trick. it's actually even proven as well. So this is something which would work for all the possible machine designs. But it's sometimes slightly tricky because the inverse of machine which accepts even amounts of A is actually, in this case, flipping the accepting states to here and to here. It means that this would accept non-even amounts of A, odd amount, and also it means 0 amount. So it's sometimes not super clear what the inverse would do with the machine. And you do have to look at it and then figure out, okay, actually it will do this thing. So the inverting is sometimes tricky. And then the last one today, actually the task 7, which was a bonus, is to build a state machine which would be counting. So it is counting, basically counting words which have less A's than B's. So we can imagine it sort of almost like a grid. If we start here, and this is a state which says I have read nothing, then you can go to, after reading A, you can go to left, and if means there is a state which means I have read one more A than B, then you could have arrow like this pointing back. And so if you read 1A, then we end up here. We want less A's than B's actually. So if you read 1A, then it's more A's than B's. So this is not useful. But then if you read B again, you get to a situation where it's zeroed out. So the same thing would happen on the right, on the inverse, where we would be accepting, or like moving into the right, I guess, with B's, and then to the left with A's. So this looks simple so far, and then something like this would be here, where this state would be accepted because it's actually something that has read just it has read 1B more than A's. So if we have a, I don't know, word which starts with A, B, B, then it's a word with less A's than B's. So we up here, so it's good. The problem becomes in terms of words which are something like A, and then B, and then maybe, I don't know, some bunch of B's. So this is a word which we would like to accept because we have less A's than B's. The problem becomes that you would have to draw the same these two arrows. So go to the right and then go back with A and then with B for all of these A's, and up in front you know how many of these the user can enter. And the way how it's defined is that, yeah, I can add the same thing on the other side. And yeah. And have this one again accepting. But this sort of just pushes away the situation for like slightly, and then we can accept more words which have less A's than B's, but still not all the possible words which can come, which are actually infinity of A's and infinity of B's, or and some mix from these as well. And that's a problem which cannot really be solved with state machines, because it cannot really work with these infinities. Because in your design you would have to have infinity of these paths going to the left and to the right. I can like write this and try to pretend that it's okay, but actually something like this doesn't work with the state machines. So the distinction, sort of what sort of machine would accept this or would be able to work with these, with basically counting, and the answer there is the Turing machines. So something which has a tape in addition. And we have not really talked about the way how Turing machines are, but I guess I just wanted to have this one bonus example as an illustration of a problem that state machines cannot really solve, and the reason why there is a need for some extension. So in the moment where you want to start counting something, you really need some Turing machine, which in addition to what we are saying, it has this, an infinitely long memory line, sort of, and in each of these slots in the memory, it can just save a value. So it actually works like a computer as well. So in that case, it's possible to design a machine which would account for infinite amount of inputs at the or like letters at the input. Right. So the answer is no, actually. No, we need a Turing machine. From so yeah, this is the end of today's class. From you, what I would like to further add is that there is the quiz that you have to fill, which is basically just adding a screenshot from today's class, screenshots of your solutions, I guess, or however far you got with these tasks. Yeah, you don't have to cheat if like you didn't get that. You don't have to copy paste it from here. I'm kind of really more about how far you go on. It doesn't really matter how far that was. There is no limit for how many files you have to load in here. So if you have some designs for the state machine project that you were supposed to be working on over the last few weeks, you can also add it here, and I can also look at it. I know that I got some mails from you guys, so I do have already some of them, but please just add it here as well. It will kind of help when evaluating you. One last thing, like a sneak peek for the next class, will be what we will be doing the next time. So we have kind of we were sort of in the middle of the class, I think. So we went through a lot of the algebra parts already, and now we will be starting a new topic, which is talking about probability and statistics, and we will look at it from the practical side of view, sort of like look at the maths behind this, but then try to apply it for some problems or some data sets that we are working on here, and connect it with statistics is also a way how to visualize some data sets or how to visualize statistics, and we will look at some plots. So for example, this is a actual plot which is being used by visualizing by Chernow's faces, is plotting some parameters to like how the face will be shaped or something. So this is one example. It's a bizarre one. There will be other ones which are less strange, but nonetheless are useful for when you are working later with some data or something. And because we will be talking about probability, we can also add some random sampling into it, and then see what sort of uses do different random functions have, and how can they be used for textures, terrains, etc.